So, hello folks, this is going to be about Cortex or how to performance tune Cortex for scale. How many of you know what Cortex is? Okay, so you're in the right room. How many of you are already using Cortex? Nice, you're gonna love this talk. So this is the Cortex deep dive. I've actually changed the title a bunch of times on my slides, and in the end I ended up with every way we DDoSed our Cortex, or how to make sure your Cortex will scale with your usage. So a little bit about me. I'm Goutham. I started as a Prometheus maintainer, and then I started working on Cortex at Grafana Labs. And now I'm a Cortex maintainer, and I also co-authored Loki along with Tom. Loki just hit 1.0, which is amazing. And Loki is also built on top of Cortex, so whatever I'm saying for Cortex also applies to Loki. So that's nice. So, how many of you are familiar with this very simple diagram? Looks small, looks simple, right? It's not. But I spent my last 15 to 18 months being on call for this beast. And it's actually quite easy to tame, and that's what I'm going to talk about. So this is the architecture of Cortex. I'm not going to do all the components and all the ways it can break, all the ways you can tame this, but I'm going to give you a framework on how you can fix things if you're running Cortex, or in general any system that is a database or a distributed database. So for those of you who are not familiar, Cortex is a horizontally scalable, distributed, multi-tenant version of Prometheus. It has all the buzzwords. And so the beauty of Cortex is its configurability. So if you actually do Cortex help, how many lines do you think are printed? Can someone take a rough guess? It's there on the screen, but yeah, it actually prints 1005 lines. That's about like 500 flags. So again, this means you can tune every single piece of Cortex individually, and we have a bunch of composable components that actually, so essentially, we have a caching component that has memcache, Redis, in-memory, on disk, and then you can use the same cache component in 6 different places. So that's like 60 or 70 flags right there. So there's a bunch of things that you can configure in Cortex, and I actually wanted to control myself help and just scroll through for like 30 minutes. But yeah, so I'm going to actually tackle two things, the write path and the read path, and how to actually make sure you are configuring Cortex for scale. So, the write path. So if you can see this, see my pointer. So essentially Prometheus writes to something called the gateway that does authentication, that adds the tenant ID, tenant header, sends it to the distributor sends it to the ingester. The ingester actually takes all these samples, individual samples, builds them up into bigger chunks, and then writes it into Bigtable, GCS, and a cache. So this is a small subset of the write path that you're seeing, and I'm just going to cover this bit of the write path now. So again, suddenly you're operating Cortex and suddenly you get paged saying the writes are failing, or Prometheus is failing to write data, or the Prometheus remote write is falling behind. It's just not able to write fast enough. So what do I do? So I've been, again, this is my playbook for being on call for Cortex. I get paged for writes. I go to something called the Cortex writes dashboard, which is actually based on the read method. So let me see if my... So how many of you have heard of the read method? So read method is this method of how to instrument your distributed applications, especially if they are RPC systems. So it says you need to track your requests, errors, and duration. So again, as I said, we have a gateway. This is the Cortex component that talks to the distributor, that talks to an etcd, that talks to an ingester. The ingester writes to memcached, Bigtable, and stuff like that. So essentially, this is like a tiered application where A talks to B, talks to C, talks to D. And you have the QPS and the latency on the QPS on the left and latency on the right. The beauty of this is, if something goes red, for example, you see the gateway is red, 500 errors are being thrown, distributor is red, but the ingester is green. So immediately you can understand the distributor is what is throwing these errors, and that you need to look at the distributor logs, not the ingester logs. So again, the same thing applies for latency. You're seeing, okay, there's like 40 millisecond latency on writes. Writes are super quick. there's a 40 millisecond latency on the distributor, and the ingester is only having a 5 millisecond latency, which means the distributor is what is adding the latency. So if you actually have distributed systems, if you can build these very consistent templated red dashboards, that will actually give you at one glance what is wrong with your system, what is right with your system. So this is our Cortex Rights dashboard where we have everything tiered. So one thing is, everything that I'm talking about here is open source. I just open sourced this today morning. I'm going to walk you through how you can get these own dashboards and alerts for you if you're running Cortex. And the next thing is, okay, everything is green but just slow. So we have a SLO of 1 second. 99.9% of our writes need to pass within 1 second. And if I'm seeing, okay, suddenly something is being limited, or like I'm being rate limited, or I'm just seeing high latency, I have a scaling dashboard. And this scaling dashboard is super important because we run Cortex as a service. And initially, I set up a Cortex, provisioned it, blah, blah, blah. And then the sales team went ahead and signed up a bunch of customers, and I forgot to upgrade my Cortex or like scale it up. And everything started to slow down, things started to boom. So I built this dashboard that does two things. One is workload-based scaling, and the other is resource-based scaling. So we'll tackle the resource-based scaling, which is the obvious one. Essentially, there are 12 replicas, but if you look at the CPU usage and CPU requests, you need 30 replicas. So I can just take one look at this dashboard and see, okay, I know exactly what is wrong here. And the other thing is, this is our dev system. This is our dev namespace, so it's intentionally under-provisioned. Similarly, we have this workload-based scaling. So if you're familiar with Cortex, you have this ingester component, for example. And the ingester component stores the recent 6 to 12 hours of data. So essentially, you send all the samples to the ingester. It batches them up to into 6-hour chunks and then writes the chunk to Bigtable or DynamoDB, just to reduce write amplification and to have compression and everything. So we actually limit the number of active series an ingester can do, because we noticed that regardless of 6 hours or 12 hours, the memory being used by an ingester is dependent on the number of active series it has. And we limit the amount of active series to 1 million to 1.5 million series. But it's all dependent on your use case and how tightly you want to run your system. So because the recent data is in the ingesters, the queryers also hit the ingesters for their queries. And this means if the ingester has too many series, the ingester will add some latency to your queries. If the ingester is just managing a smaller number of series, the queries are going to be quicker. And even during rollouts, we need to actually transfer this live in-mem data to the new ingester that came up, so that we don't partially flush things. So the transfers are also faster. Having said that, you need to get comfortable with a number and then stick to that number. So Brian from Weaveworks, he runs the Cortex with 4 million series with 64 gig RAM, while we run it at 1 million series with 16 gig RAM. So these are all trade-offs that you need to make, but just make sure that you're scaling along with usage. So the moment you tell your users, hey, we have this cool system called Cortex, you can send all your metrics here, they'll be stored forever, people will send you a shit ton of metrics. So make sure that you have alerts on all of this, and then make sure you can scale. So you can't just stare at dashboards all day. You need to actually make sure that you're paged for this. So we have alerts for everything. So essentially, the other thing we do is we make sure we cache the recent 2 days of data in memory in memcached, so that most of your queries are going to be on the recent 2 days. So if you open a dashboard, it's going to be last 24 hours or last 48 hours. And most dashboards are just last 1 hour. So we noticed that 99.9% of our queries are actually only looking at the recent 2 days of data. It's the rare query over 30 days that looks at the older data. So we wanted to make sure that everything is in cache so that it's super fast. And also it reduces the load on the remote system like GCS or Bigtable. So we have an alert that says, okay, based on this time series and these many chunks being generated, you need these many memcaches. Do you have enough? Do you have, are you sure you're only running at most 1.5 active time series per ingester and stuff like that? So the good thing is, the first 3 alerts are actually warning alerts, so you don't get paged. So I get a Slack notification. Who's on call, there's a channel. It's the duty of on call to keep a look at that channel and make sure that if there's too many warning alerts, to go debug, to go scale up. So all this care the on-call person takes care of it. But the last one is actually a paging alert. Let me just remove this. Go away. Let me see if that works. So the last alert is actually Cortex memory, Cortex hitting its memory limits. That's because, no. So this is a paging alert because, again, as I said, the recent 6 hours of data is in memory in the ingester, and we don't want the ingesters to So if suddenly somebody is sending too many metrics and the ingester memory is just growing, we get paged saying, okay, the ingester memory is growing, you might have data loss. The next thing is we also have SLOs and SLAs and SLIs for everything, including our read and writes. So you should watch beyond stock on how to do SLOs right. So we have a 6-hour error budget, 1-hour error budget, and 1-day error budget. So we have all these error budgets written down, and our SLOs are public. It's just that our queries should be 99.9% of our queries should be faster than 2.5 seconds and successful, and 99.9% of our writes should be successful and slower than 1 second. So we have all these SLO-based alerts. So if something's wrong in the write path, I'll get alerted within 15 minutes, and then I can go take a look at my my writes dashboard, and then I can start debugging things by looking at logs or traces and stuff like that. So this is actually the easy bits, the write path. How do I get access to all these nice alerts? So we actually open sourced our JSONet in the morning. So yes. So this repo has actually the JSONet for generating all the YAMLs for deployments. The JSONet only currently supports the GCS or Bigtable and Cassandra backends, not the AWS backend. We're going to add the AWS backend, remove some Grafana specific bits, and then put it into the Cortex project open source. And if you want to look at the alerts, it's in the Cortex mixin. So the README has instructions on how you can generate these alerts. But again, these are our windows. So it's like, if you, like, again, there's this nice blog on how to do alerting on SLOs. So we use that blog and say our latency threshold is 2.5 seconds for read. And then we have a bunch of alerts. Like if the ingest is unhealthy, it's a critical alert pages. Flushes are being stuck with pages. But if requests are failing for 15 minutes, we have warnings. So things like that. So we have both warning and critical alerts, and warnings don't page, but it's the job of the on-call person to keep an eye on that. So all of this is open source. All of this you can get. So go get some alerts and monitoring. And also check out the nice way of how to package dashboards, alerts, recording rules, and the YAML together in the form of JSONet if you're not familiar with it. So we recently had an HCD outage. We had an outage for 2 hours. Where we just couldn't accept writes. That's because our HCD suddenly decided it didn't have a leader. And the funny thing is, as I said, we have this nice dashboard that was talking to the gateway, talking to the distributor, talking to the HCD. We recently added HCD, but did not forgot to add this panel in the dashboard. So when writes were failing, we had no clue why they were failing. But that's why you do postmortem, so that you can fix your mistakes. And now we actually have the panel. Let me see where that other dashboard is. So if you look at it, during the time of the outage, we just couldn't write stuff, and our HCD just became red everywhere. So, yep, we make mistakes, but we do postmortems and we fix them. So that's the write path. The read path is trickier because, the read path is super tricky because there's just too many components, and the tricky part is the queries vary in size. Sometimes somebody sends a query that queries 1 million time series over 50 days of data, and that's bound to be slow. And then there's other queries that, that's life. You can't make it any faster than 20 seconds. I mean, we are trying to, but you don't want to be paged for that. On the other hand, if somebody sends a simple query that just looks at 1 time series over 5 days of data, if that is taking 10 seconds, you want to be paged for that. So we don't have a good way to page on the size of the query and latency, so we page for everything. And turns out we are fast enough, quick enough, so that we are rarely paged. Like, I'm on call right now, I think. I'm actually on call in the Indian time zone, so I'm not on call right now. I'm on call tonight. But yeah, if you look at the read path, you get Grafana sends a query to the query front end talks to the courier talks to ingester, the databases, and a bunch of caches. So this is the reads dashboard. I just want to quickly walk you through the reads dashboard. But once you have the reads dashboard, so it's like the gateway, the query front end, the caches, and then the courier and stuff like that. It's the same thing. So for debugging queries like this in a distributed system, especially something that is latency sensitive, you need the right tools, and I found Jaeger to be super powerful. So first thing is you need your dashboards and you need your alerts to tell you something is wrong, but to actually debug what is wrong, you need Jaeger. And I really like Jaeger, and it's also super simple to configure Jaeger into Cortex. You just need to add a bunch of environment variables. Like these 3 environment variables are needed. Actually, only the first one is needed, but we do dynamic sampling and we add some extra metadata to each of our containers. So we add a bunch of extra flags. And this is a variable that we import and we just add it to our container wherever required. So if you so again, there's instructions on how to use the JSONet, but if you just set the Jaeger agent host, automatically all your Cortex deployments will be sending traces to Jaeger. Again, JSONet is cool, but if you're not using JSONet, just set these environment variables. So again, Grafana talks to the query front end talks to the courier talks to the data sources, caches, and a bunch of things. So it's a complex system. So I'm assuming I'm getting paged now for query latency. So I'm just going to walk you through the dashboards that I take a look at. First is the Cortex reads dashboard. While that loads, let me load the others also. Yep. The Cortex reads dashboard, so this is like the gateway, the front end, the courier, the ingester, memcache lookups, and Bigtable. So this is over the last 24 hours. I actually intentionally did a huge query that took a long time, 1.5 minutes. And this won't immediately page me, but that's because it's just one query. You don't want to be paged for a single query. If I consistently do these queries, and it's consistently so, that's when I'll get paged. That's when I'll exhaust my error budget and I'll get paged. I'll be like, okay, so the gateway is seeing 1.5 minute latency. The front end is seeing 1.5 minute latency, so it's probably not the front end, not the gateway. Caches, okay, caches are quite quick. The courier is seeing significant latency, 1 minute, so the front end is adding 500 milliseconds of latency. The ingester is also kind of slow. So the courier makes several calls to the ingester, so it's kind of hard to see where the latency is coming from. And in the end, we can see that Bigtable itself is taking 21 seconds average to respond to each lookup. So it probably means Bigtable is overloaded. That's because I know that exactly why Bigtable is overloaded and stuff. Because I've been doing this for 18 months, just with one look I can tame this. So this is the reads dashboard that can kind of at a high level tells me what is slow. The good thing is you should all, for those of you who have not heard of the red method, you should go check out the red method because that tells you how to build these consistent templated dashboards. And then I have the Cortex queries dashboard that actually tells me exactly higher level data about the queries that are being run. Okay, so suddenly I see that my query queue had 60 things piling up, which probably means that is what that was significant. So we saw that the front end was having 1.5 minute latency, but the courier was having 1 minute latency. So the 500 milliseconds was being added by the querying. So that's how you can figure things out. And you can see, okay, my front end cache hit rate is super high. I'm seeing a bunch of cache misses, cache hits. So you can see how different caches are performing, how the churn rate is. And a bunch of query related things that actually helps you understand are these queries big or are these queries slow. You can see that most queries are only taking 10-20,000 chunks a query, but suddenly there was a query that was taking 190K chunks. Probably there was a huge cache miss in the chunk cache, and that is causing extra load on the Bigtable. So again, this is another dashboard that helps me figure things out. And in the end, I also have a memcache dashboard that tells me exactly what the eviction rate is, command rate is, what's the latency, memory being used, and all of that. So I use these 3 dashboards to kind of understand at a high level what is going on and if I can figure out at one glance. If that doesn't work, and usually it doesn't, I use Jaeger. Sorry about that. So, how many of you are familiar with Jaeger already? How many of you are seeing Jaeger for the first time in action? Okay, so you're gonna love this demo. So I'm just gonna pick a service, the Cortex query frontend, and I'm gonna say, I want the API prom. This is the query endpoint, and I want to see all the requests that took more than 1 second. The min duration is 1 second, and I'm seeing a bunch of requests, so let me look at this one that took 30 seconds. So let me zoom in a little bit and then expand this. So this is a live demo. Again, I have a perfect trace before, but let's see why this query is taking 37 seconds. Hopefully the demo gods are with me. So you can see that most of the latency is being introduced by the PromQL eval function in this. And if I look at the PromQL eval function, so the other problem with Jaeger is when it's overloaded, it drops traces. So it dropped a bunch of traces that was not telling me how much each function call is. So that's a good thing because I actually have an example perfect trace already ready. The demo is not with me this time. But yes, so I can see that this particular query took 16 seconds. Let me see if the cache was a hit or not. Okay, it tried to look if this has been requested before. There was a cache miss. So it tried to, went into the retry middleware, and then we have this taking 16 seconds. If you look at it, PromQL prepare function is taking super quick, but the PromQL seristore.get function is taking 14 seconds. Let me see why it is taking 14 seconds. So there's a function called getChunkRefs that is taking 12 seconds, and then there's a bunch of functions. So in this function, you can see that something is taking 12 seconds. Out of that, you can see that most of the function is being done by this query pages function that's taking 11 seconds. If I expand that, I can see, let me expand this a little bit more. That big table is actually taking 7 or 8 seconds to respond to each query, each table lookup, each row lookup, and that is adding a significant delay to my latency. So I can go back, look at big table, see that it's under provisioned, and then provision big table. So this way, by using Jaeger, by getting alerted by my alerts, missing SLOs, I look at dashboards, kind of try to figure out what's wrong. And if it's not clear, I then use Jaeger to kind of just dive into exactly what's wrong. So I spent 7 or 8 months just like in a query optimization sprint. So I made sure that the code is instrumented with the right functions so that for an operator, it's easy to figure out what's wrong. So again, if you're on the read path, the things that you need to look out for is, are your caches doing well? Are your backend stores doing well? And if both of them are doing well, you probably are only running 10 queries to handle 200 queries per second. You just need to make sure that you're not queuing up your queries, you're scaling things up. Again, use the scaling dashboard to scale things up. So let me see, okay. So that's the read path debugging, write path debugging, and in the end, Cortex is a multi-tenant system. So we run one big cluster for all our US customers and one big cluster for all our EU customers. And the idea is one customer should not DDoS everyone else. Just make sure that you limit everything. So again, there's a bunch of limits, but the idea is you keep the default limit super low. So essentially, we run Cortex as a hosted Prometheus service, and if you sign up, you get super low limits. So only a small Prometheus will be able to send data to it. But the moment you hit these limits, we get an alert, and then we reach out to you, we understand your use case, and we'll tell you, okay, it's gonna cost you this much, are you ready for it? And then I increase his limits, or increase the tenant's limits. So there's a bunch of limits that you need to take care of. One is, what is the samples per second that each distributor can handle? And what is the number of maximum series that each ingester should have per user? And sometimes somebody has a histogram that sends us like 300, 400,000 metrics for a single metric name. And we don't want that. That's usually a bad practice, and we want to tell our users, hey, we're limiting this because this is a bad practice, are you sure? So that's the max series per metric. And then there's some query level limits that you need to use. When you're querying, you need to make sure that they're not querying 100 million time series or like 5 million time series over 30 days of data. You need to make sure that they're not oobing all the queries for everyone else. So there's a bunch of query limits. So again, a bunch of these flags that you saw in Cortex, they're like 30% of them are just limits, because we want to make sure that one user cannot DDoS everyone else, but we also want to be super flexible for weird use cases. We'll see that. So again, I said make sure that every single user has a default low limit, but make sure you increase that thing. So Cortex is able to override the limits per user. And how we, again, we use JSON to template this out because we have hundreds of users and we don't want to set every one of them by hand. So we have this overrides variable that you can just add. Okay, initially everyone is a small user by default. And suddenly, okay, they say, okay, we have 2 Prometheuses, or we have a high cardinality Prometheus. We graduate them to a medium user. We just add it to this variable, and there's a config map that's updated that Cortex takes up. This is all at runtime. And you can see that you can make them a medium user, but also give them specific configuration. For example, we had a user with a specific use case that required the user to send metrics with 40 label names. Like our default is 20 for a good reason. And then there was this user trying to send everything in a Kubernetes annotation in this metric for a good reason. So we reached out to them and told them we're dropping this metric because it's too many labels, and then they explained that to us. And then this actually, you can see how easy it is for us, operators, to manage this complexity. We're like, okay, he's a big user, but he gets this extra limit added that is overridden and stuff like that. And if you actually look at the config map, it looks like this. For user 29, these are the limits and stuff like that. So how do we do the tiering? So we have these variables. Again, all of this is open source in the JSONet. I think if you're going to have teams or tens of teams using Cortex in your organization, make sure that you have some kind of manageable config management. Like you don't want to spend 3 days to do something small. So we have these tiers: small user, medium user, big user, and if you have a lot of money, you're a super user. Yep. And that is actually not the end of the things. So there's a bunch of query limits. How many of you attended Tom's talk yesterday on blazing fast PromQL? Nice. Okay, that's a significant portion. So I highlighted something like this because when I first found it, it totally blew my mind. And then I was like, who did this magic? And it turns out it was me a long while back. So there's the same limit, which is max query length 744 hours or 7 days, and max query length 500 days, set in 2 different deployments. So what is happening? What is this max query length? So the max query, so when you get a range query or when you get a PromQL query, it is the length of the data that you look at. So that if it's like rate 3 minutes or like rate 5 minutes in an instant query, it's 5 minutes of data. If it's rate 5 minutes over 30 days in a range query, it's 30 days plus 5 minutes of data. So that's the max query length. And you want to make sure that a single user doesn't query too much. But you also want to make sure, hey, they're storing 13 months of data in Cortex. They should be able to query it back, of course. So how do you do this? So turns out these are 2 very different query workloads. Range request that takes over 90 days for rate 5 minutes is actually quite simple to do, while rate over 90 days is hard to do. Because in a single window, you need to look at all the 90 days of data. While in fact, with the rate, with the first example, you actually only look at 5 minutes, and then 5 minutes, and then 5 minutes, and then 5 minutes. So the memory requirement, the CPU requirements are quite low. But for the other one, it's super high. So you want to be able to limit your users to only do maybe like over 30 days, give me the increase over the last month so that I can do some billing. But also be able to do, give me rate 5 minutes over the last 13 months because I'm storing 13 months of data. So to enable that, we have the query frontend. So what the query frontend does is when you have a 30-day request, it splits it up into 31-day requests and runs it in parallel so that the queries are much faster. So If you actually compare Cortex V vanilla Prometheus, Cortex is much faster. One, because we do caching. Two, because we massively parallelize your queries. If you actually send a year-long query, it's actually run in parallel for in 365 different queries if we have them, but it's queued because we don't have 365 queries. So now in the querier, if you set the maximum query length to be 7 days, and in the query frontend, if you set it to be 500 days, it makes sense because the query frontend will let you do a query over a year. It will split it up into smaller parts and send the smaller part down to the querier. But in the querier, if you have a 90 day, you don't want to the querier, so you can only look back only 7 days. Does it make sense? So we are making sure the limit on the querier and on the query frontend is different. That allows you to do long queries, but not super intense queries. You also want to have cardinality limit on the queries. Sometimes people send like 5 million time series and they want to query all of them back together, and that will your querier. So there's this cardinality limit and max samples that you need to look out for. And after that, you also have caching. So these are two important things that we did. So this is one thing is because all the recent data is in the ingesters, you also need to query the ingesters and query the store, and then merge those two things in the queries. And we actually have hundreds of QPS, and every single query was actually going to the ingester. That means the ingester was locking up because it was always trying to select the data and stuff like that. So the ingester was adding a lot of latency to the query layer. So we decided, okay, but a lot of these queries don't need to look at the ingester because the ingester only has recent data, and these queries are old based on the dashboards. Because again, remember, we're always splitting things up into 1-day queries. So if somebody opens a 30-day dashboard and has 5 panels, the first 5 queries will look at the ingester, and the other 29 queries will not look at the ingesters. But you need to tell the queriers how much data the ingester has. So we have 6-hour chunks, so we set it to 12 hours just in case. So any query that's older than 12 hours will not hit the ingester. The other thing is we do a lot of index caching. So the index is in Bigtable, Cassandra, DynamoDB, you name it. And it's a lot of data. We do a lot of index caching, but caching the index is actually quite hard because you cache the index and then you write to the data store again, which means the cache is invalidated. So we used to do a lot of hoop jumping to make sure that we can make the cache is fresh and stuff. But once we did that, we still couldn't cache for more than 15 minutes. So if the same query is run in less than 15 minutes, it used to hit the cache for the index. But now you have another flag that is added that says, we know that any index that is older than 36 hours is stale index, that it's never going to be returned to, so just cache that forever. So if you actually cache that and reduce the load on ingesters, your queries are going to be really, really fast. So that actually made a lot of difference. So, yep. In summary, make sure you have the right alerts and dashboards that help you when you get paged. And don't get paged for every single thing. Make them all, make 99% of the alerts warning alerts. Be paged only on SLOs. Be paged on some very critical things like HCD master not HCD not having a leader for 5 minutes. That should be a paging alert. So just make sure the number of things that page is extremely low, but there are things that you should look at, make them all warning alerts. And so we do, at Grafana, we do weekly on-call, so I'm on-call for a week. And while I'm on-call, half my job is to clean up the config, do this tech debt cleanup. And I keep a look on these warning alerts and make sure that they don't fire anymore. Again, have proper SLOs, and I love these SLO alerts because once we moved to SLOs, everything changed because we have strict SLOs now. Before we used to page for every random thing. Whenever somebody opens a big dashboard, you get paged. But now, only if the 99.9 percentile of the requests are slower than 2.5 seconds, I get paged, and that's super rare now with all the caching that we do. Scale up with the usage. Again, this is a mistake a lot of people make. They forget to scale their clusters up, but just keep on onboarding teams. And once they have an onboarding document, teams onboard themselves, and they don't even tell the operators, which is good. But you need to make sure that you scale up your cluster along with that. Jaeger is amazing. It saved my life. Before Jaeger, we were basically guessing, looking at the stars and guessing, okay, this might be slow because of this. We had no context. But now, and then we used to deploy something, add a bunch of metrics. It used to be marginally faster, but it didn't fix anything. You're like, okay, we are 0.3% faster. That's nice. But now with Jaeger, I know exactly what is slow or which function is slow. But even while doing that, just don't add Jaeger traces everywhere. Like, have them at higher level functions, and only if that function is slow, like if you can't debug things, then go to a lower one. Because Jaeger like traces are kind of expensive. Just don't have too many spans or every single function call in there. And then don't forget to limit stuff. If this is a multi-tenant environment, and yeah, just make sure everyone has the right limits, and also have a framework to make sure that managing this limiting configuration is easy. Like for us, we have tiers. Instead of individual limits for each tenant, we have tiers, and we have like hundreds of customers that, yeah, I like the current config management solution that we have. All of that is open source, by the way, so you can use it directly or you can look at it and you can build your own. So, any questions? Yep. I want to see if we have a mic.
Do you auto-scale anything based on time load?
Oh, yes. So, good question. So, we have a scaling dashboard. Why not auto-scale, right? Yep. The thing is, the ingester is a stateful component, and auto-scaling it is not trivial, but it's a work in progress. We are working on auto-scaling the ingester. So the idea is the ingester has 6 hours of data in memory, and when a new ingester comes up, it transfers the 6 hours of data into that. And then it dies and stuff, so that you don't put extraordinary load, because you need to flush 1 million series or 4 million series, and each series has 6 different rows that need to be, so you need to do 6 million writes if you want to like kill an ingester. So this process is kind of fragile, and you can only do it one at a time. It's a pain. Having said that, we are working on fixing that right now. So there's a PR open that fixes this. Once that is there, you can auto-scale. Good question. Yep.
When you measure the query runtime, do you offset the time spent on the Prometheus server?
Query runtime. So okay, that's a good question. So we don't use remote read. So people directly query Cortex. So they just set their data source in Grafana to be the Cortex endpoint that we give them with authentication. So they never, there's no Prometheus on the query path. Any other questions? Yep. You have to shout.
Yeah. About like managers, how you're handling right now the initiative in this case? Do you have many instances of managers and products?
Okay, so good question. So so we have Cortex, and then we have a Prometheus scraping this Cortex that's doing our alerting, and then we have a global alert manager cluster in 2 different, maybe 3 or 4 different clusters. There's an alert manager each that is talking to each other. That's we have a global alert manager cluster, and this Prometheus is sending alerts to that alert manager, and that's paging us. Any other questions? Cool. Thank you.